The winter hit different at 8,000 feet in the Wind River Mountains. Yakov Petrov learned this his first December in 1884 when frost formed inside his cabin walls and his water bucket froze 3 feet from his wood stove. He had built exactly like every homesteader was told: tight logs, iron stove, plank floor, wooden bed frame, standard, and trusted. By February, he had burned through more wood than 2 men should need, yet still woke shivering while neighboring cabins fought the same losing battle against the mountain cold. That spring, Jacob quietly applied his grandfather's old world masonry techniques to build what neighbors mocked as a foolish clay oven bed. While their cabins stayed cold and ate through cord after cord of firewood, Jacob slept warm through sub zero nights using half the wood. In the next few minutes, I'll break down the exact steps and principles behind this forgotten heating method. What did Jacob understand about storing and releasing heat that every serious cold climate builder should know? The accepted wisdom across the high country followed a simple pattern that seemed to make perfect sense. Build fast, build cheap, get shelter before the snow flies. Every homesteader manual and territorial guide preached the same gospel. Frame your cabin with whatever timber you could fell and drag, lay a simple stick floor over rough joists, throw up plank walls, and drop a cast iron stove in one corner. The Sears catalog promised that their Model 7 wood burner could heat any cabin up to 400 square feet, and most settlers took that promise as frontier law. Jacob had followed this wisdom precisely. His cabin measured 16 by 20 feet with 7-foot walls, chinked with mud and moss between the logs. The stick floor sat on joists spaced 4 feet apart with gaps wide enough to lose a coin through. His iron stove, hauled up from Cheyenne by wagon train at considerable expense, sat in the northwest corner with a straight pipe chimney punched through the roof. A narrow bed platform built from split pine planks occupied the opposite corner, raised 18 inches off the floor on log supports. Every neighbor for 20 miles had built essentially the same structure. The problem started before December ended. On clear nights when the temperature dropped below zero, the interior walls sweated condensation that froze into sheets of ice by morning. The plank floor transmitted cold so efficiently that standing barefoot for even seconds became painful. Worse, the cast iron stove created a brutal temperature gradient. Within 3 feet of the firebox, the air became uncomfortably hot while the far corners of the cabin remained below freezing. The bed platform, positioned away from the stove to prevent fire risk, stayed so cold that Jacob woke each morning stiff and aching despite piling on every quilt and blanket he owned. His neighbors suffered identical failures. Thomas Brennan, whose cabin sat half a mile down the valley, burned through his entire winter wood supply by early February and had to start breaking up furniture to keep his family warm. Mary and Samuel Curtis reported that their baby developed a persistent cough from sleeping in the perpetually damp, cold cabin air. Most disturbing, old Henrik Larsson's roof began sagging under the snow load because the cabin's interior stayed so cold that no heat rose to melt the accumulating ice. Jakob possessed knowledge that set him apart from most frontier settlers. His grandfather, Dmitri Petrov, had been a petchmaker in the Carpathian Mountains of what would become Romania, building massive masonry stoves that heated peasant cottages through winters far harsher than anything Wyoming could deliver. As a boy in Pennsylvania, Jacob had heard endless stories about these old-world heating systems. Dmitri would describe clay and stone ovens that weighed several tons, with elaborate internal channels that captured heat from cooking fires and stored it in the masonry mass. Families would sleep on benches built directly into these stoves, staying warm all night from a single evening fire. The local homesteading community viewed such stories as old-world nonsense. When Jacob mentioned his grandfather's techniques at the monthly community meeting in Brennan's cabin, the response was immediate mockery. "We ain't building castles here, Jacob," Thomas Brennan declared. "We're trying to survive, not show off with fancy European contraptions." Samuel Curtis added that masonry work required lime mortar and skilled stonework that simply didn't exist on the frontier. "Besides," Curtis continued, "who's got time to haul tons of rock when there's land to clear and crops to plant?" Yet Jacob observed something his neighbors missed. The fundamental problem wasn't the cold itself, but how quickly heat disappeared from their cabins. Cast iron stoves heated air rapidly, but provided no thermal storage. The moment the fire died down, all that heat vanished up the chimney or leaked through the countless gaps in their light construction. The stick floors, raised on joists with air circulation underneath, actually helped cold air flow throughout the cabin. The thin plank walls offered virtually no insulation, and the minimal thermal mass meant temperature swings of 40 degrees or more between a roaring fire and cold ashes. Jakob began sketching ideas in a leather-bound journal his grandfather had given him years before. Instead of heating air that immediately escaped, what if he could heat a mass of stone and clay that would hold and slowly release warmth for hours? Instead of a raised bed platform that stayed cold, what if the sleeping surface sat directly on or against a heated mass? His grandfather's stories included detailed descriptions of families sleeping warmly on clay-covered stone benches that stayed warm until morning from evening cooking fires. The technical challenge lay in adapting Old World masonry techniques to frontier constraints. Dimitri's Pech stoves used fired bricks and lime mortar, materials unavailable in the Wind River Mountains, but the region offered plenty of fieldstone, and Jakob knew how to mix clay-based mortar from local materials. The principle remained the same: create a massive heat storage system using internal flue channels to capture exhaust heat before it escaped the chimney. His neighbor's skepticism ran deeper than mere practicality. The frontier mentality prized speed and simplicity above all else. Heavy masonry work seemed to violate the essential spirit of homesteading, which demanded mobility and minimal investment in permanent structures. Many settlers expected to move on once they proved up their claims, making elaborate heating systems appear wasteful. The idea of sleeping on stone and clay struck them as primitive, even barbaric, compared to proper wooden bed frames. Jakob recognized that he was challenging more than building techniques. The accepted frontier approach represented a complete philosophy: minimal materials, maximum speed, temporary solutions for temporary people. His grandfather's masonry tradition assumed permanence, patient craftsmanship, and investment in long-term comfort over immediate convenience. The conflict cut to the heart of how people thought about survival itself. Through January and February, as his neighbors burned through cords of precious firewood while still shivering through bitter nights, Jacob quietly gathered field stones and began experimenting with clay mixtures. He would test whether Old World thermal wisdom could solve New World heating problems, or whether frontier skeptics were right that such methods had no place in the practical business of mountain survival. By early March, Jacob had collected enough fieldstone to begin construction. The rocks varied in size from fist-sized chunks to pieces weighing 50 pounds or more, all gathered from a talus slope 2 miles east of his cabin. He selected dense, hard stones that wouldn't crack under repeated heating cycles, avoiding any rock with visible cracks or soft, crumbly surfaces. The clay came from a deposit he discovered along the creek bed, a blue-gray material that became plastic and workable when mixed with water, but dried to concrete hardness. The foundation required demolishing a section of his existing stick floor. Jakob pulled up the pine planks and dug 18 inches into the frozen earth, creating a rectangular pit measuring 8 feet long by 4 feet wide. He lined this excavation with a base layer of small stones, then mixed his first batch of mortar using 3 parts clay, 1 part sand, and chopped straw for binding strength. The mixture had to achieve precise consistency, wet enough to flow between stones, but thick enough to support weight without slumping. Construction began with the firebox, positioned at one end of the foundation. Jakob built this chamber using the largest, flattest stones, creating an internal space roughly 2 feet wide, 18 inches deep, and 20 inches high. The firebox walls rose 12 inches above ground level, with an arched opening facing into the cabin. This opening measured 14 inches wide by 10 inches high, deliberately smaller than the interior chamber to create proper draft and combustion conditions. The revolutionary element lay in the flue system Jakob designed within the masonry mass. Instead of allowing hot exhaust gases to escape directly up a chimney, he created a labyrinth of channels that forced the smoke and heat to travel a circuitous path through the stone mass before exiting. Starting from the back of the firebox, the first channel ran horizontally along the base of the structure for 6 feet, then turned upward through a vertical section, then horizontal again in the opposite direction, creating an S-shaped path through the interior of the mass. Each channel measured roughly 6 inches square, large enough to prevent blockage, but small enough to ensure maximum contact between hot gases and surrounding stone. Jakob formed these passages by laying flat stones as channel floors and walls, then covering them with more flat stones before adding the next layer of masonry above. The work required constant attention to maintaining proper dimensions and smooth transitions to prevent turbulence that could disrupt draft. The most critical technical innovation involved the sleeping platform integration. Rather than building a separate bed frame, Jakob constructed the sleeping surface as an integral part of the heated mass. The final layer of masonry extended beyond the firebox area, creating a flat platform measuring 6 feet long by 3 feet wide. This surface sat directly over the horizontal flue channels, with only 4 inches of stone separating the sleeper from the hot exhaust gases flowing beneath. The platform required careful engineering to distribute weight properly. Jakob used large, flat capstones, some weighing over 100 pounds, to create an even sleeping surface. Between these stones and the flue channels below, he installed a layer of smaller stones packed with clay mortar, providing thermal mass while protecting the structural integrity of the gas passages underneath. Clay mortar proved essential for creating airtight joints throughout the system. Jakob discovered that pure clay cracked as it dried, so he experimented with different additives. His final mixture combined 4 parts blue clay, 2 parts sand, 1 part chopped grass, and 1 part wood ash from his stove. This combination dried without major cracking and created gas-tight seals between stones. He applied the mortar thick between joints, then smoothed the interior channel surfaces to prevent soot buildup and maintain proper gas flow. The chimney connection required precise calculation. Jakob positioned the final exit port at the highest point of the flue labyrinth, 18 inches above the sleeping platform. From here, a vertical clay-lined channel rose through the cabin roof, sized at 8 inches square to provide adequate draft without excessive heat loss. The entire flue path from firebox to chimney exit measured approximately 24 feet, ensuring maximum heat extraction from the exhaust gases. Testing began on a mild evening in late March when outside temperatures hovered around 20 degrees Fahrenheit. Jakob built a small fire in the firebox using dry pine kindling and split aspen logs. Within an hour, he could feel warmth radiating from the stone platform. The flue system drew properly, with no smoke entering the cabin and steady draft pulling combustion gases through the labyrinth. The thermal performance exceeded his expectations. After the fire burned down to coals, the sleeping platform surface measured approximately 90 degrees Fahrenheit when tested with his hand. More significantly, this warmth persisted through the night. When Jakob woke 12 hours later, the stone surface still felt noticeably warm to the touch, measuring roughly 70 degrees Fahrenheit by his estimation. Fuel efficiency proved equally impressive. The evening's fire consumed approximately 1/8 cord of split wood, including the initial heating period. His cast iron stove, by comparison, required constant feeding throughout cold nights, and typically burned through 1/4 cord of wood for similar heating duration. The masonry system's ability to capture and store heat from the combustion gases meant far less thermal energy escaped unused up the chimney. The completed mass weighed approximately 2 tons, including the fieldstone, clay mortar, and sleeping platform. This enormous thermal capacity meant the system heated slowly, but also cooled slowly, providing steady warmth release over extended periods. Unlike his iron stove, which created rapid temperature swings as fires built up and died down, the masonry mass moderated these fluctuations through its heat storage capacity. Jakob's neighbors noticed the reduced smoke from his chimney and the smaller woodpile beside his cabin, but few understood the technical principles at work. Thomas Brennan commented that Jakob seemed to burn less wood, but assumed this meant insufficient heating. The true test would come during the next severe cold snap, when the thermal mass system would face conditions that regularly defeated conventional frontier heating methods. The masonry bed's effectiveness revealed a critical weakness in Jakob's cabin envelope. While the heated stone platform provided sustained warmth directly beneath the sleeper, heat radiated into the cabin's airspace, only to escape immediately through countless gaps in poorly insulated surfaces. On calm nights, the system worked reasonably well, but when wind picked up, cold drafts infiltrated through every crack between the logs, around the door frame, and through the gaps in his stick flooring, carrying away the precious thermal energy faster than the mass could replace it. Jakob identified the primary heat loss mechanisms through careful observation during April's variable weather. Cold air entered the cabin through the spaces between logs, which had been chinked only with mud and moss the previous autumn. This temporary chinking had dried, cracked, and partially fallen out during the freeze-thaw cycles of winter, leaving gaps up to 2 inches wide in places. Additional infiltration occurred around the door, which fit poorly in its frame, and through the single window, where the glass sat loosely in a rough wooden frame without proper sealing. The solution required a systematic approach to air sealing that drew on techniques Jakob had observed in Pennsylvania German farmhouses during his youth. These settlers, many of German and Swiss origin, had developed sophisticated methods for weatherproofing log structures using materials available on the frontier. The key innovation involved creating a secondary thermal barrier using clay-based plaster applied directly to the interior log surfaces. Jakob began by preparing a new chinking mixture far superior to his original mud and moss approach. He combined 4 parts of the same blue clay used in his masonry work with 2 parts sand, 1 part chopped straw, and 1 part cow dung obtained from a neighbor's cattle. The organic matter provided binding strength and prevented cracking as the mixture dried. This improved chinking was packed deep into the gaps between logs, pressed firmly with wooden tools to eliminate air pockets, and smoothed flush with the log surfaces. The revolutionary step involved applying a continuous clay plaster coat to the entire interior wall surface. This technique, which Jakob remembered seeing in the homes of German immigrants, created a thermal mass layer that absorbed heat from the cabin's air and re-radiated it slowly over time. He mixed the plaster using 3 parts clay, 2 parts fine sand, and 1 part finely chopped grass, adding just enough water to achieve a consistency that could be applied with his hands and smoothed with wooden floats. Application required working in sections during warm afternoons when the clay would dry properly. Jakob spread the plaster approximately 1/2 inch thick across the log surfaces, pressing it into the wood grain to ensure proper adhesion. The technique demanded patience, as rushing the work created air bubbles and weak spots that would crack and fall off. Each section took 2 days to cure completely, during which Jakob had to maintain consistent cabin temperature to prevent rapid drying and cracking. The window and door sealing presented different technical challenges. For the window, Jakob created a double barrier system using available materials. He first sealed the gaps around the glass with a mixture of pine pitch and clay, heated until workable and pressed into place with wooden tools. Then he constructed removable interior shutters from split pine boards, designed to fit tightly against the window frame on cold nights. These shutters included a layer of wool batting salvaged from damaged clothing, creating an insulative airspace between the glass and the interior. Door sealing required precision fitting that tested Jakob's carpentry skills. He trimmed the door frame to reduce gaps, then created weather stripping using strips of wool felt pressed into grooves carved along the frame edges. A heavy wool blanket hung on pegs provided additional sealing during the coldest nights, though this made entry and exit inconvenient. The most innovative element involved addressing heat loss through the floor. Jakob's stick flooring, raised on joists with open-air circulation underneath, created a massive cold bridge that undermined the entire heating system. He solved this by installing a vapor barrier and insulative layer beneath the floor structure. Using birch bark gathered from nearby groves, he created overlapping sheets that blocked air movement between the floor joists. Over this barrier, he packed dried grass and pine needles, creating an insulative layer approximately 6 inches thick. The thermal performance improvements became apparent within days of completing the envelope work. The clay plaster walls absorbed heat during evening fires and continued radiating warmth for hours after the combustion ended. More significantly, The improved air sealing eliminated the cold drafts that had previously robbed heat from the masonry bed's thermal output. The cabin now maintained more consistent temperatures throughout its interior space, rather than the extreme hot and cold zones created by the original iron stove setup. Jakob discovered an unexpected benefit of the clay plaster walls during a rainy period in early May. Unlike the bare log surfaces, which absorbed moisture from humid air and developed mold growth, the clay surfaces actually helped regulate humidity levels inside the cabin. The clay absorbed excess moisture during damp periods and released it slowly when conditions became dry, creating a more comfortable and healthier indoor environment. Fuel consumption dropped dramatically with the improved envelope. Where the masonry bed alone had reduced wood usage by approximately 50% compared to the iron stove, the combination of thermal mass and proper sealing achieved savings of roughly 70%. A single evening fire now provided comfortable temperatures throughout the following day, even during cool spring weather. The integrated system demonstrated principles that individual components could not achieve alone. The masonry bed provided thermal storage, but without proper envelope control, much of that stored heat was wasted. Conversely, air sealing and insulation alone could not provide the sustained, even heat distribution that the thermal mass delivered. Together, they created a heating system that outperformed conventional frontier methods, while using significantly less fuel and providing superior comfort. This combination would face its ultimate test when the next winter brought sustained sub-zero temperatures and relentless wind to the high country. As spring turned to summer, Jakob discovered that his masonry heating system created new challenges that conventional iron stoves never faced. The complex flue labyrinth, while excellent at capturing heat from combustion gases, also provided numerous surfaces where moisture could condense and soot could accumulate. During humid weather, condensation formed inside the stone channels, creating conditions that could lead to structural damage and poor air quality. More critically, improper fire management could fill the labyrinth with creosote deposits that reduced efficiency and created serious fire hazards. The chimney design required immediate attention. Jakob's original 8-inch square chimney, adequate for his previous iron stove, proved insufficient for the masonry system's complex gas flow requirements. The lengthy flue path created resistance that demanded stronger draft to pull combustion gases through the labyrinth effectively. When atmospheric pressure dropped during storm systems, backdrafts pushed smoke into the cabin, indicating inadequate chimney height and cross-sectional area. Jakob rebuilt the chimney using principles he remembered from discussions with a traveling mason who had passed through the valley the previous summer. The new structure rose 24 feet above the cabin roof, constructed with carefully selected flat stones and high-quality clay mortar. Internal dimensions measured 10 inches by 12 inches, providing 30% more cross-sectional area than the original design. Most importantly, Jakob lined the interior with a smooth clay wash, mixed with fine sand to create a surface that promoted laminar gas flow and resisted creosote adhesion. The chimney's base required a specialized smoke chamber where gases from the flue labyrinth could gather and accelerate upward. Jakob constructed this chamber directly above the final horizontal flue section, creating an expanding volume that allowed combustion gases to slow down, deposit remaining particles, and then accelerate smoothly into the vertical chimney shaft. This design eliminated the turbulence that had caused backdrafts and poor draw in his original system. Fuel selection and preparation became critical factors that conventional frontier heating had largely ignored. Iron stoves could burn almost any combustible material, from green wood to trash, though inefficiently. The masonry system demanded carefully chosen and prepared fuel to achieve complete combustion and minimize deposits in the flue channels. Jakob developed a systematic approach to fuel management based on techniques his grandfather had described for European masonry stoves. Hardwood species proved essential for optimal performance. Jakob focused on splitting oak, maple, and ash. When available, avoiding softwoods like pine except for kindling purposes. Hardwoods burned hotter and more completely, producing less smoke and fewer volatile compounds that could condense as creosote in the flue system. He split all firewood to uniform thickness, approximately 3 to 4 inches, ensuring consistent burning rates and complete combustion. Seasoning requirements exceeded typical frontier practices. While settlers commonly burned wood cut the same season, Jacob discovered that his system performed best with wood dried for at least 18 months. He constructed a dedicated woodshed with open sides and a slanted roof, allowing air circulation while protecting the fuel from direct precipitation. Properly seasoned wood contained less than 20% moisture content, burned with minimal smoke production, and generated maximum heat output per pound. Fire management techniques revolutionized Jacob's approach to heating. Rather than maintaining continuous low-intensity fires like iron stove users, he adopted a batch burning strategy that maximized combustion efficiency. Each evening, he built a single intense fire using dry kindling and split hardwood, allowing it to burn completely to coals before adding the next fuel load. This technique achieved temperatures hot enough for complete combustion while minimizing the smoldering conditions that produced creosote. The timing and sequence of fuel loading required precise attention. Jacob started each fire with fine kindling arranged in a grid pattern that promoted airflow, then added progressively larger pieces as the fire established. Once the firebox reached full intensity, he loaded the maximum fuel quantity the chamber could accommodate, then sealed the firebox opening with a cast iron door he had fabricated from salvaged stove parts. This approach created a controlled burn that consumed all available oxygen efficiently while maintaining high temperatures throughout the combustion cycle. Ventilation management addressed moisture control and indoor air quality concerns that the sealed envelope had created. The improved air sealing eliminated natural infiltration that had previously provided fresh air exchange, sometimes leading to stuffy conditions and moisture buildup. Jacob instituted a systematic ventilation routine that balanced fresh air needs with heat conservation. Each morning after the fire had burned to ash, Jacob opened a small window on the cabin's leeward side for exactly 15 minutes, allowing moisture-laden air to escape while drawing in dry outside air. This brief ventilation period removed overnight humidity from cooking and respiration without significantly cooling the thermal mass. During extended periods of damp weather, he extended these ventilation sessions to prevent mold growth on organic materials inside the cabin. Ash removal became a weekly maintenance ritual critical to system performance. Unlike iron stoves where ash could accumulate for long periods, the masonry firebox required regular cleaning to maintain proper airflow and prevent ash from blocking the entrance to the flue labyrinth. Jacob removed ash when it reached approximately 2 inches depth, using a long-handled wooden shovel to avoid damaging the clay mortar joints in the firebox floor. The ash itself proved valuable for multiple purposes beyond disposal. Mixed with water, wood ash created a caustic solution effective for cleaning the chimney's clay lining and removing light creosote deposits. Jacob also used ash as an additive in his mortar recipes, where the potassium compounds improved the clay's durability and water resistance. By midsummer, the refined system operated with remarkable efficiency and safety. Proper fuel selection and fire management eliminated the smoke infiltration and poor combustion that had plagued the early versions. The enlarged chimney provided consistent draft regardless of weather conditions, while the systematic ventilation routine maintained healthy indoor air quality without wasting thermal energy. Jacob's neighbors began noticing the complete absence of visible smoke from his chimney, even during periods when everyone was burning fires for cooking. The clean combustion and effective heat capture meant almost no wasted thermal energy escaped as visible exhaust, a stark contrast to their own chimneys that produced steady streams of smoke throughout the day. This efficiency would prove decisive when winter returned, and fuel conservation became a matter of survival rather than mere convenience. The test arrived in December of 1885 when an Arctic air mass settled over the Wind River Mountains and refused to move for 6 weeks. Temperatures plummeted to 30 below zero Fahrenheit and stayed there, accompanied by winds that drove the effective temperature even lower. Snow accumulated to depths of 4 feet on the level, with drifts reaching 8 feet against north-facing walls. This sustained cold snap pushed every heating system in the valley beyond its design limits and separated effective methods from mere theoretical improvements. Thomas Brennan's cabin became a laboratory for conventional heating failure. His cast iron stove, adequate for normal winter conditions, consumed firewood at an alarming rate while struggling to maintain interior temperatures above freezing. Brennan burned through his entire winter wood supply by mid-January, then began breaking up furniture, barn siding, and fence posts to keep his family alive. Even with continuous feeding of fuel, frost formed on the interior walls each night, and the family huddled together under every available blanket while still shivering uncontrollably. The Brennan family's water supply illustrated the cascade of problems created by inadequate heating. Their wooden water barrel, positioned 3 feet from the stove for convenience, froze solid during the coldest nights despite the nearby fire. Melting ice for Azovstal. Drinking water required burning precious fuel, creating a vicious cycle where survival activities consumed resources needed for warmth. Food storage became equally problematic as root vegetables froze in their cabins' cold corners, ruining weeks of preserved supplies. More dangerously, the extreme cold revealed structural weaknesses in conventional log construction. The Curtis cabin, built with standard techniques, developed severe settling as the logs contracted in the sustained freeze. Gaps opened between wall logs despite previous chinking efforts, allowing cold air to pour directly into the living space. Samuel Curtis spent entire days re-chinking gaps with frozen mud and snow, but the repairs failed as soon as the materials froze solid. Most critically, snow loads threatened several cabins with structural collapse. The Curtis and Brennan cabins, with minimal interior heating, provided no thermal protection for their roof structures. Ice dams formed along the eaves where snow accumulated, creating tremendous weight loads that caused roof beams to sag visibly. Henrik Larsson's cabin actually suffered partial roof failure when one support beam cracked under the combined load of snow and ice, flooding the interior and forcing the family to shelter with neighbors. Jakob's system responded to the extreme conditions with remarkable stability and efficiency. His evening fire routine continued unchanged throughout the cold snap, requiring approximately 1/8 cord of split oak to maintain comfortable interior conditions for 24 hours. While neighbors burned furniture and outbuildings, Jakob's woodshed remained well stocked, with fuel consumption running 70% below his neighbors' emergency consumption rates. The thermal mass demonstrated a previously unobserved benefit during the sustained freeze. The massive stone structure created thermal inertia that resisted rapid temperature changes, moderating the extreme swings that plagued conventional heating systems. When outside temperatures dropped from 0 to 30 below overnight, Jakob's cabin interior temperature declined only 5 to 8 degrees Fahrenheit compared to 20 to 30 degree drops experienced by neighbors using iron stoves. Interior climate control revealed the system's sophisticated thermal management capabilities. The clay-plastered walls absorbed excess heat during peak firing periods and released it gradually as outside temperatures plummeted. This thermal buffering created remarkably stable interior conditions with temperature variations of less than 10 degrees throughout each 24-hour cycle. The sleeping platform maintained surface temperatures between 70 and 90 degrees Fahrenheit regardless of outside conditions, providing comfortable rest without the multiple blanket layers required in conventional cabins. Water and food preservation demonstrated practical advantages that extended beyond mere comfort. Jakob's cabin maintained interior temperatures consistently above 40 degrees Fahrenheit, preventing freezing of stored water and preserving root vegetables throughout the cold snap. His wooden water containers never froze, eliminating the fuel waste associated with ice melting that plagued his neighbors. Preserved foods remained accessible and usable, reducing the caloric stress that accompanied survival heating in other cabins. The masonry system's impact on roof performance proved equally significant. Heat radiating from the thermal mass created an interior temperature differential that prevented ice dam formation and reduced snow load accumulation. The cabin's roof remained relatively warm compared to unheated structures, causing snow to sublimate gradually rather than building up dangerous weight loads. While neighbor cabins battled ice dams and structural damage, Jakob's roof maintained its integrity throughout the freeze. Most remarkably, the system's efficiency actually improved during the coldest conditions. The extreme temperature differential between interior and exterior enhanced the chimney draft, improving combustion efficiency and heat extraction from the flue labyrinth. Complete fuel combustion during peak cold conditions meant virtually no waste heat escaped up the chimney, maximizing the thermal energy captured by the stone mass. By late January, neighboring families began visiting Jacob's cabin to escape the brutal conditions in their own homes. Mary Curtis brought her children for afternoon visits, marveling at the comfortable interior temperatures and the absence of drafts or cold spots. These visits provided stark demonstration of the system's effectiveness, as visitors could immediately feel the difference between sustained, even warmth, and the blast furnace heating of conventional stoves. Samuel Curtis became the first convert, approaching Jacob in early February to learn the construction techniques. Curtis had watched his own fuel supplies dwindle while Jacob's remained stable, and his cabin's structural problems convinced him that conventional methods were inadequate for mountain conditions. Jacob shared his grandfather's masonry knowledge freely, helping Curtis plan a similar system for reconstruction after winter's end. Henrik Larsson, whose cabin had suffered roof damage, committed to completely rebuilding using Jacob's thermal mass principles. Thomas Brennan, facing potential fuel exhaustion, negotiated to purchase seasoned hardwood from Jacob's surplus supply in exchange for labor assistance with future construction projects. The extreme conditions had transformed skepticism into desperate interest in proven alternatives. Word of Jacob's success spread beyond the immediate valley through mail correspondence and traveling supply wagons. The territorial newspaper in Cheyenne published a brief article describing the European heating methods being tested in mountain homesteads, though without technical details. Supply. Merchants began receiving requests for clay-working tools and masonry materials from previously uninterested customers. The sustained freeze broke in early March, but its lessons permanently altered local building practices. 3 new cabins constructed that spring incorporated masonry heating systems based on Jacob's design, with modifications suited to individual sites and available materials. The thermal mass approach had proven itself under the most severe conditions frontier builders could face, establishing efficient heating as a practical necessity rather than old-world luxury for mountain survival.